Welcome, grade 10s. We're going to do another lesson on wave, sound, and light. We are now going to look at longitudinal waves and sound. Previously, we had looked at transverse pulses. We looked at transverse waves. Okay, and there's a lot of things I'm going to remind you of about that, but today we're going to look at another wave, which is longitudinal wave. First thing we need to do is let's talk about what I want you to be able to do by the end of this lesson, okay? So let's think about the key concepts. In terms of longitudinal waves, you need to be able to give me a definition of what a longitudinal wave is. So the definition is going to be very important, but it's like everything else. Then you're going to have to give me important terminology, and by that we're talking about things like what is amplitude, wavelength, all of those things, and I'm sure you remember those from transverse waves. Then we're going to look at some calculations. It's a wave, which means it's going to have a wave speed, just like our transverse waves did. So we're going to need to do calculations. But what's the point of a longitudinal wave? Well, a very, very important longitudinal wave is sound. And in fact, we're very grateful that we have these longitudinal waves. Otherwise, you'd just be looking at a screen, and I would just be using my hands and looking silly because you wouldn't be able to hear me. All right, so sound is really important. Within that, what do I need you to be able to do by the time we're finished today is we're going to look at certain things to do with sound. Things like the properties of sound. What makes sound special? What can we do with sound? Things like that it is a longitudinal wave. Okay? That it can be reflected. It's got wonderful things that we can use it for. That comes into the applications, but us as humans apply to a lot of things besides just being able to hear things. But animals are so clever when it comes to the use of sound. And then we're going to need to do some calculations, just like with the longitudinal waves. Okay, so we've got a lot to get through, and I'm hoping you're going to hang in there with me. I'm going to show you some interesting things, and hopefully you're going to actually enjoy sound. Sound is actually one of my favorite things to teach. I really enjoy it. Let's get on to what a longitudinal wave is, okay? Now, I'm hoping you remember from when we did transverse waves, and I'm just going to quickly draw this in, is with a transverse wave, we remember that we have a position of rest, and then on that position of rest, we get a transverse wave that does this, okay? And we remember this is like water waves and that sort of thing, and that with a transverse wave, our particles of our motion go up and down, the particles of whatever medium it's going through, but the wave goes sideways. Okay, and those mediums are things like string, air, water, all of that sort of stuff. So this was our nice transverse wave, which we did last time. Remember, our amplitude was the distance from the top of a crest to a equilibrium position or the rest position, or it could have been to the bottom of a trough. We spoke about positions in phase, where we have, for example, this position over here and this little x over here. Those are 2 points on my wave that are in phase because they're going to do exactly the same thing at the same time. And then that distance between them gives me the wavelength. Okay, so now we have a whole bunch of things that are important inside the transverse wave, but the biggest thing I wanted you to see is that it is the one where the particles move up and down, but the wave moves sideways. But what about a longitudinal wave? In the last lesson, we also looked at using the slinky spring, and I'm going to remind you what those are. It's these little things, okay? And I have a nice, this one actually is my favorite too because it's small. And this, when I do this with my slinky spring, I'm actually creating a little bit of a longitudinal wave, okay? Because of the way the particles are moving, because we're forcing them to come close together and then further apart and then close together and then further apart, close together. Remember, that doesn't happen when it's a transverse wave, it does this. We need to look at something a little more detailed for you. So what we're going to do is we're going to look at a quick video clip where we're actually going to show you a longitudinal wave moving with a slinky spring, okay? So I want you to watch. we're going to show it as pulses. Okay, do you remember that when we first started transverse waves, we first looked at a transverse pulse. So we looked at the fact that we could make one at a time. That's what we're going to do here first. We're going to show you a longitudinal pulse, and then when there's a whole bunch of those, that becomes a longitudinal wave. So if you watch it, watch carefully, because the person creating the wave for us creates a pulse. They move their hand backwards and forwards, backwards and forwards. And if you watch carefully, and you can see that the wave, there's positions, like at the moment, if you look in the middle, you can see that there's a part where the particles are far apart, and then there's a little piece when they're close together. Okay, and if we carry on watching, it keeps doing that. The particles get close together, they get further apart. They get close together, they get further apart. That is a longitudinal wave. Because what we have is, and it's what I showed you just now, is that the particles go far apart and then they come close together. Go far apart and they come close together. And that's how the energy moves from one end to the other, because this particle moves backwards and forwards, getting bigger and smaller all the time. That is our longitudinal wave. So if we go back and we look at the definition of a longitudinal wave, okay, and this is really, really important, it is a wave where the particles in the medium, sound, water, whatever, move parallel to the direction of motion. I cannot say that they move in the same direction of motion, because if you were watching carefully, you would have seen that they actually go backwards and forwards. But the pulse moves along the slinky. Okay, so the pulse moves in one direction, but the actual particles move backwards and forwards. Sometimes that's a little hard to see with the slinky. So we're going to go back and we're going to look at a animation, which is going to show it really nicely. Now, what I want you to do when you look at this animation is we have a yellow dot on the animation. That yellow particle is the same as one part of the slinky, okay? I want you to watch carefully how it moves, because that's what we're really looking at. So if we look at the yellow dot, the little white particle comes along, transfers its energy to the yellow one, which then transfers its energy to the white one, and the yellow one moves backwards and forwards. So we're getting a situation where the pulse is moving towards the right as you're watching your screen, but our little particles are moving right and left, right and left. Now this is really slowed down, so it makes it easier for you to see, but they go right and left, right and left. That is really important for us, because what I'm showing you is that there's a displacement, and I'm hoping what you picked up as you were watching that is that the yellow particle doesn't just keep going on and on and on and on forever, but it has a definite, it gets to a certain position, then it stops, then it comes back, goes to the other side and stops, comes back, goes to the other side, then stops. What is it doing? It is having a maximum displacement. So if we now look at what we learned in transverse waves, where we had the concept of amplitude, which was the maximum displacement from the rest position, we get exactly the same here. It's just a little more difficult to see. So when we go back to the video, at the moment, the yellow particle is in its rest position. The dark lines down the center of the screen that you can see are the rest position. We let it play. Okay, now it's displacing, and right there, that is its maximum displacement. The yellow particle is moved to the right. It is displaced. Then it's going to change direction. It goes back to rest, which is what we expected. We saw that with transverse waves. And then it moves to the maximum displacement in the opposite direction. So each of my particles has a maximum displacement from rest, and it goes through the cycle. So it goes one way, goes through rest, goes another way, through rest, goes the other way. Same with what we had with our transverse waves. When it would go up and down, it was just a bit easier to see because you could see the motion. That's really important to us, because what we've now discovered is that a longitudinal wave has an amplitude. That's brilliant. But it can't have a crest or a trough, because if we just look for a little while longer, you'll see that's just moving backwards and forwards, so we don't have that nice up and down motion like we had in transverse wave. So how does that help us? Because we've got this amplitude, great, but amplitude for what? How do I know where a maximum is or a minimum is? How does this help me when I'm trying to look at the wave and look at what the wave is made out of? So let's look at what happens when we have lots of particles, and it's going to be a little bit easier to see. We're still looking at an animation, and now we're going to build in a couple of extra terms because we can't use crest and trough. So here we go. So we're looking at the sound particles, and now we've got a whole bunch, and if you look at them, it's actually really nice. I'm hoping you can see this shows really nicely that we have a whole bunch of particles that get close together and some that get far apart. Now right there is a compression. That is a situation where we have the particles in my medium that are now close together. They are compressed. That is almost like thinking of a trough or a crest. Not quite, but it's a position in the wave. So we don't say it's a crest, we don't say it's equal to a trough, but it is a position where we have maximum squishedness. That's a good word for this. The particles are compressed. They are squished together as far as they're going to go while the wave moves. Okay, so they're as close together as they're going to get. They've been compressed. Then we have another position. So if we watch again, the particles are going to move, okay, in a second, because the compression has still been shown. And over there, we have a rarefaction. Now, this is a strange term, and you would think, well, what's the opposite of a compression? It's definitely not a rarefaction, but that's what the term is. And what that means is that now the particles are far apart. They've been stretched. Okay, now they're as far as they're going to go. This also represents a place of maximum displacement, but it's not a trough or a crest either. It's just a position where we can see that the particles are either close together or the particles are far apart. Okay, so we get our compression and we get our rarefaction. That's really important. So if we watch for a little longer, you'll see that we will always have a rarefaction, and next to it is a compression. And if you actually look closely to the screen, you get the fact that we have the rarefaction, compression, rarefaction, compression, rarefaction. Always happens like that. Okay, but let's define those terms because those are great, but you know, what do we do with them? Well, if we go back and we're going to look at some of the important terms. First of all, the compression. It's a region where the particles, let's do that, are closest together. Now, this can be a little difficult to draw. If you're like me, you're not an artist, and drawing little slinky springs and stuff is just really difficult, and we don't do that because, you know, it's just embarrassing, especially on national television. So when we represent our wave, we do this. We draw it with lines, and our compression is the position, which I'm drawing now, where we have our lines close together. This represents a wave, all these little lines together, and then they come back together, we get a compression. They don't go skew, but that's okay. So what that means is, over here, that's a compression. Particles are close together. Okay, every longitudinal wave has to go through that process. What about the rarefaction that we spoke about? Well, when we define that, it's when they're furthest apart. It's the position where we move them away. Okay, that's brilliant. When we draw it, so we're going to do the same thing, and I'll make them a little wider. Ooh, sorry, we'll try and make them go straight because we know that's what they're going to do. So here they go. Ooh. Apparently, they also like to do all sorts of things, and we get our rarefaction. Now, in class, if you're ever asked to draw a wave, please make sure all your lines are the same length. It's a little harder for me, but you make sure all your lines are the same length, because actually what I'm showing you is that for some reason my slinky got wider or fatter along the way, which we know can't happen. Okay, and then they get wide again, and then they get thin again, but the point is, this is my rarefaction, okay? Widest part. So we have two important parts. How does that help us though? Because now we know they come close together, they go far apart. But you know, in terms of describing waves, when we looked at transverse waves, we never really considered what the amplitude of the wave meant for us, or what the distance between the rest position and the crest meant. It didn't make much sense. And in fact, in our calculations, we never even considered amplitude, which means finding the wavelength of the wave is really important. Now, things get a little sticky with a longitudinal wave, because if we're looking at my diagram in particular, which isn't great, you're probably going, oh, wow, where do we find wavelength? First of all, we need to go back to how we defined wavelength as a transverse wave, because that's really important. Remember, wavelength is the distance, let's do this, between two consecutive points in phase. Okay, great. And here we have a really nice representation of a slinky spring. And essentially what we've done, because it's much easier to identify it, is we're taking the wavelength as from the beginning of one compression to the beginning of another compression, because then it's quite easy to see that those particles, if they've just gone through the compression phase, are now going to come out into the refraction phase. So beginning of a beginning of a compression, 2 points in phase. So there's lots of wavelengths, and it doesn't actually matter, but it's sometimes difficult to see. So let's go back to the animation we were looking at for our points in phase. Okay, let's go back to the animation I showed you earlier, and now we're going to look. Now, as you watch this animation, I want you to take very careful note of the yellow particles, okay? Because they are very, very special, and I want you to watch the yellow particles as they move. So we're going to quickly watch the animation, and we watch the yellow particles, it has moved, and now can you see as you watch this, and we'll do it slowly, the yellow particles are quite close to the side. They're both moving sideways. They're now going past to the right. They've gone past the equilibrium position, and then they're going back, and they're going to go left, and we're going to keep on. We're not going to worry about the compression at the moment, but the point is with those yellow, did you notice that they were both going backwards and forwards and backwards and forwards at the same time? They were in phase. Those yellow particles with any of the white particles would have been out of phase. So we can't use those as wavelengths. But the yellow particles, absolutely that's where the wavelength is. So that's where we get the wavelength from, which is really important for us, because wavelength is what we're going to use for calculations. Excellent. You're going, okay, this makes sense. Okay. Now, what about amplitude? We've spoken about amplitude a little bit, but let's define it. Amplitude is your maximum displacement from equilibrium. Longitudinal waves have a little bit of a little added thing here. It says this would be the maximum increase or decrease in pressure from the equilibrium position. Why are we talking about pressure? Because when you were watching the animations, you noticed that the particles move close together, far apart. They moving close together like that causes pressure, just like you learnt in gases and all sorts of things along the way in science. So that causes pressure. So either we're going to have a big pressure or we're going to have a little pressure when they move far apart. That's why we have to put it in there, because it's what happens when the wave moves, when the energy moves, it's an increase in pressure to the particle in front of it. So the pressure increases, gets transferred, then it decreases, then it transfers to something else. So our amplitude is not just maximum displacement, but maximum increase in pressure from equilibrium, and that causes a compression. So if we increase the pressure, we get compression. If we decrease the pressure, we get a rarefaction. Okay? Amplitude is going to become quite important when we look at sound waves, which we're going to do a little later on today. But we're talking about waves. Okay, longitudinal waves have wavelength, amplitude, but they're a wave, so surely they have period and frequency. Absolutely. Same as what we learned with transverse waves. So longitudinal waves, the period is the time taken, one wave, nothing difficult about that. Frequency is the number of wavelengths per second. Wow. And look here. Frequency equals 1 over frequency. Maybe not. Frequency equals 1 over period. Period equals 1 over frequency. Same as what you've done before. Remember, Period is a time. So period is measured in seconds, okay? And it's on the board, but it's okay. I'm just reminding you. Seconds. Frequency in hertz means per second. Those haven't changed. Wow. All the same things we had when it came to our longitudinal waves. That brings us to having to do calculations. And I think your little brains have had lots of information put into them. So what we're going to do is I'm going to give you a short break. Go get a glass of water. Make sure you've got a pen and paper and a calculator. And when you get back in a couple of minutes, we're going to do some calculations with longitudinal waves. Okay? So we'll see you in a couple of minutes. Welcome back, and I hope you're ready. So before you went away and we had a little bit of a leg stretch, we said we're going to look at some calculations. We're still dealing with waves, so we are going to use the wave equation. It's not changed. It's still valid for waves. And remember, the wave equation is speed equals wavelength times frequency. Great. Remember, speed is measured in meters per second, wavelength in meters, and frequency in hertz. So we go, we can do this. Nothing has changed from what we did with transverse waves in terms of measuring things. So let's do a couple of questions, okay? First one, this is just to see whether we understand the difference, is the question is a multiple choice one and says, which of the following is not a longitudinal wave? Light, sound, or ultrasound? Well, first we're going, I don't know. Well, let's realize that two of these answers have the word sound in them. That means they must be related, okay? And I've already said to you today that sound is an example of a longitudinal wave, which means ultrasound, and there we're talking about sound that we cannot hear. And we're going to talk about it a little later on. So ultrasound is a really, really fascinating part of the sound spectrum that does wonderful things for us as humans. It's everywhere. That means it's a longitudinal wave, which means the one that is not a longitudinal wave is light. That was nice and easy. Now that's how you work out your multiple choice when you go to tests and exams, grade 10s. Don't just pick a letter because you can. Think through what your choices are, okay? Now, question 2. Now it says, which of the following media, that is plural for medium, okay, can a longitudinal wave like sound not travel through? Let's talk through these as well. Think about a solid, okay? You've all, I'm sure at some stage, watched an old western, old movie, and you've seen people who go, so they want to know if the train's coming, and there's all that scary music in the background, and what do? They put their head on the railway track, because what they're doing is they're trying to listen for the sound of the train, because they'll hear it through the railway track before they hear it through the air. So that means solids absolutely conduct electric current. What am I talking about? Solids absolutely conduct sound. So that's not my answer. Let's think about a liquid. Okay, you go swimming, you go play in the pool, and everyone's done this at some stage, and you decide you need to speak to your friend who's on the other side of the pool underwater. So you start shouting at them. They hear something. They can't really distinguish what the noise is because their ears aren't designed to hear underwater, but they can still hear the sound. Or when you're in the bath and you put your head under the water because you don't want to hear the fact that your brother is moaning at you about something, or whatever the case may be, you can still hear because sound travels through a liquid. So my answer is not B. What about a gas? Well, hopefully you're going, of course it travels through a gas. If it didn't, we wouldn't hear anything because we're surrounded by a gas. We're surrounded by air. Air is a gas. So we know it travels through a gas. Well, that leaves us a vacuum. And now, I'm hoping some of you are going, but it does travel through a vacuum. We've watched movies, especially in space, where they blow something up or they shoot a laser and you hear it. That's because it's a movie. Movies would be boring if they blew stuff up in space and you couldn't hear the explosion. you hear it because it makes the movie more exciting, but in reality, you wouldn't hear it. If you are out in a vacuum, in space, and your spaceship blew up for some reason, which would be a disaster, you would not hear it, because sound needs a medium. It needs something to travel through. So this is an important thing here. Sound does not travel through a vacuum. We don't experience that on Earth because it's very difficult to create actual vacuums on a planet. So we don't really experience that. And our life experience in terms of watching TV and movies and all of that sort of stuff doesn't help because, like I said, they have to make the ship blow up and you hear the sound. Or if you're watching a science fiction movie and they're having a space war and you don't hear the little laser guns going, you're not going to watch it because it's going to be boring. Okay, so we won't do that. Now, let's get on to the calculations. A longitudinal wave has a compression to compression distance. Important piece of word, important information. Compression to compression distance of 10 meters. That is going to be important. It takes the wave 5 seconds to pass a point. Also an important piece of information. So now the first question here is, what is the wavelength of the longitudinal wave? And now we go, hang on, wait, I know this. Wavelength is defined as the distance between 2 points in phase. And right at the beginning, when I showed you the first diagram of a wavelength, we said, well, it can be from the beginning of a compression to the beginning of the next compression. Beginning of a rarefaction to the beginning of a rarefaction. Whatever that might be. Here they're telling me that the distance between the front of a compression and the front of the next compression is 10 meters. My wavelength is 10 meters. That was nice. We like questions like this. Now they ask for the speed of the wave. So, we've just worked out wavelength is 10 meters. I'm going to need frequency, maybe, and velocity, because really those are the ones, that's the information we would use. We would use velocity equals frequency times wavelength. Now, what they said to us is it takes 5 seconds for one wave to pass a point. What are they giving us? They're giving us period. Because remember, period is the time taken for one wavelength to pass a point. So they're saying to you, period is 5 seconds. Cool. How does that help us though? We know the relationship between period and frequency. Frequency is 1 over period, which means it's going to be 1 over 5, and 1 divided by 5 is 0.2 hertz. Let's put that in here. Now, and this is a personal thing for me, I like to underline an answer I put in because then I remember I had to find that out. Because if we can at all avoid using something we've worked out earlier on, just in case we made a mistake, then that's what we do. But here we're going to have to use what we've worked out. So now I know that my frequency is 0.2. I know the wavelength. We can do this. Velocity is wavelength times frequency. So we have 10 times 0.2, and that gives me 2 meters per second. It's actually quite a slow wave in reality. When we look at in big terms, it's quite slow, but that's okay. Let's do one more question. Here it says, a flute, which is a musical instrument, produces a musical sound traveling at a speed of 320 meters per second. The frequency of the note is 256 hertz. That's quite a high note, okay? First thing they ask is calculate the period of the note. Okay, well, I have frequency. Okay. Now, remember, frequency is the number of waves that pass a point in 1 second. So if I'm telling you that the frequency of this wave is 256 hertz, what I'm saying to you is that if we could actually see this, which we can't, we would see 256 waves, little waves, go past me in 1 second. It's incredibly fast, okay? First thing they want is the period, so let's look how long it takes for one wave to go past. Period, 1 over frequency, so it's 1 divided by 256, and we get, let's just quickly work it out, because 0,03, ooh, pen, 0,0039 seconds. It's tiny. Okay, very quick. We expect that. Okay, if you'd got an answer here of 1, I'd be worried. Always double check your answers. Now they want the wavelength of the note. Earlier in the question, they gave me the speed, 320. I don't want to use period because I had to work it out just in case we got it wrong. Frequency is 256 hertz, and they want wavelength. We can do this. This is actually quite nice. Velocity is wavelength times frequency. We have 320, which then equals wavelength times 256. Remember from maths, in order to get the wavelength on its own, I'm going to divide both sides by 256. In your exams and tests, grade 10s, you don't need to show the step. I'm just showing it for those of you that struggle with the changing of formula, and that's fine. Okay, you really don't need to show this. So the 256 disappears, which means wavelength is actually 320 divided by 256, and we get 1,25 meters. That's quite a long wavelength. I think that explains, okay, 1,25 meters is, well, it's about the width of my arms, sort of, maybe a little bit less. That's a long wave, okay? And think about the fact that I'm saying to you that this wave, which is about this width, okay, is probably a little bit more, is moving 320 meters every second, because 256 of these go past a point in 1 second. It's moving very, very fast, but it's sound. It's different to what we normally use for longitudinal waves. We can hear that. It has to move that fast for us to hear it, okay? And that actually brings us to where we're going to go now, which is sound. Sound is such an interesting part of longitudinal waves, and in fact, inside of your curriculum, the only way we really deal with longitudinal waves is within the sound system, okay? That was not meant to be, that came out wrong. But that's okay. So within the sound, we only look at it within sound. But how do we produce sound? Where do we get sound from? Now, I brought some toys into the studio today because, like I said, sound is one of my pet loves. I really enjoy it. How do we produce sound? Now, there's lots of ways to produce sound, and the diagram I'm going to show uses a tuning fork. Now, tuning forks aren't used that often anymore outside of science laboratories. Musicians and stuff use one of these little things, which I'm going to use in a second, which is an electronic tuner because it's just easier. Okay, and they can hook up to all sorts of things, and we can do stuff with them. So, now, this is almost like a tuning fork. It's a triangle. And what we're going to do is I'm going to produce sound from it. But in order to get sound, I need to hit it. Okay? And you can hear it vibrates and the sound changes. But before I get a sound, there needs to be contact. We need to hit it. But I can change the sound I get by changing what I use. So it's slightly different. Okay? It's a slightly nicer sound, actually. But it depends on what I'm using. But what's happening is this metal is vibrating. Now, we get the sound we get from these because of the type of metal that's used, the shape that it's in. You get triangles of all sorts of sizes and thicknesses and that sort of thing. And even our little batten thing that we used to hit on the triangle, these change size and thickness, as you can see from the two I have. Okay? The thick, heavy one produces a much heavier sound, whereas my smaller one produces a much lighter sound, okay, which is a bit easier on the ear. But there has to be contact. What is actually happening here? Let's go to my diagram. What is happening here? And it's the same concept as when I have a tuning fork. When we hit a tuning fork, the little fork parts of the fork vibrate. That vibration causes air particles around it to start moving. And those air particles are first going to be compressed together, then they'll move far apart, then they'll be compressed together, then they'll move far apart, and then they'll be compressed together. This causes a longitudinal wave because we have these compressions and these rarefactions. But we can experience that longitudinal wave because of the way our ears are designed. Okay, we have funny little hairs in our ears that pick up the sound and then transfer it into electrical energy, which is how our brain perceives it. So we're able to hear it. But what needs to happen is there needs to be a movement of air particles. Okay, that movement of air particles doesn't just happen randomly. So it's not a case of, well, today it feels like it's going to move in this way, and tomorrow, because it can, it's going to do something else. When I hit my triangle with my little buttons, I'll get the same sound every single time, okay? Those are very metallic sound. Same thing is these are called claves, okay? These are made from wood. But now if you listen, it doesn't give that metallic sound. This is a much duller sound. But that's also because I'm holding it. So if I hold it too tightly, I change the noise completely. But that's because when I hold them tightly, I'm not allowing the wood to vibrate. The wood has to be allowed to vibrate in order to get a nice sound. Those are quite high pitched. These are quite nice. It's a much lighter wood. You can hear that better. But I can change the sound, make it very dull. Okay? Like these are like drumsticks, okay? Very dull, because I'm holding them, I'm stopping them from vibrating, so the air around them doesn't vibrate as much. When I do this, it's a much lighter sound, because the air can vibrate around them. Okay? So, well, how fast does sound travel? Why does it seem like sometimes your friend can be right next to you and you're not hearing anything, or they can be on the other side of the room, at times you can hear things? Why is it that at night you seem to hear much better than you do during the day? Because sound travels at different speeds. It's not a constant. Light travels at a constant speed in a vacuum and in air. It's about 3 times 10 to the 8 meters per second. Sound doesn't. There isn't a constant. Okay? Now, if we look at sound, and I've got a table here for us to look at. This is the speed of any sound particle, any sound energy in different substances. If we have a piece of aluminium, sound will travel at 6,420 meters per second. It's extremely fast, but it's a metallic substance, okay? Being a metallic substance, the particles are close together. It's easy for the energy to move. In a brick, like a household brick, 3,650 meters per second. In copper, like those copper bracelets you get, 4,760. Through glass, 5,100. Through gold, 3,240 meters per second. Lead, 2,160. Now, aluminium, brick, copper, glass, gold, lead, all solids, moving very, very quickly through solids. Next, we have seawater. In seawater, it travels at 1,531, and it's a liquid. The salt helps there with the density. Then we get to air. Now watch carefully. At 0 degrees Celsius, so when it's really cold, 331. At 20 degrees, which we consider room temperature, 343 meters per second. Look at the difference between a liquid and a solid and a gas as to how quickly the sound travels. Now you're probably thinking, but I don't hear the same underwater or through a solid. You don't. We're not talking about the quality of the sound here. I'm not talking about whether you can make out somebody's words or make out that it's a definite frequency or anything. And we're not talking about that. We're talking about how fast the energy moves from one thing to another. The reason that us as humans struggle with solids and liquids is because we're not designed to hear in those mediums. Our ears are designed and they function to hear in air. So that's what we need to hearing. I am now going to show you an animation to help you explain this a little bit, okay? Now, as we watch this animation, it's not going to run for too long. watch the particles. The gas is at the top, they're not moving a lot. Then we have the solid in the middle, they're moving a bit faster, but then in a solid, they're moving even faster. And that's really important for us because that movement is what determines how quickly they're going to move. In a gas, our particles are far apart. It takes a long time for them to get to the next one. So the energy takes a long time. In a solid, in a liquid, they're slightly closer together, the spaces between them are less, so it doesn't take quite as long for the energy from one particle to move to the next one, so it moves faster. In a solid, our particles are closely packed together. Because they're closely packed together, it's easy for the sound to travel from one to the other, so it moves faster. Temperature of gases plays a very big role. You saw in the table that at 0 degrees, sound travels at 331. At 20 degrees, it travels at 343. It's still air. But if you remember from chemistry, when we increase temperature of a gas, we're increasing how much the particles are moving. They're getting all excited, okay? Because we're increasing their temperature, the particles move faster. Because they're moving faster, they're able to transfer their energy quicker, which is what we like. Transfer energy much, much quicker than when it's colder. So it's very important when we do calculations, do not make an assumption about the speed of sound here, please, grade 10s. It's not constant. It all depends on the temperature and also the type of gas. The type of gas makes a difference. So in any question, you should actually be given the speed of sound unless they want you to calculate it, okay? But where do we use this? Because that's all well and good, but where do we actually make use of this? Because we've got the sound, we know that it does things and it moves and it's a wave, but how's that important? Well, think about, first application, you go into your school hall and it's a big empty room. No one's there. What's the first thing you really like to do? You scream at the top of your lungs because you can. And what do you notice? There's an echo. You hear yourself. Not completely clearly, but you do hear yourself. What that means is, what's actually happening is the sound you've produced from your vocal cords has traveled to the walls of the hall and then bounced off. It got reflected, just like light gets reflected. And you can then hear yourself again. Sound is able to be reflected. Now, you don't hear that when there's lots of people in the hall because they absorb the sound, okay? And they're quite soft. We're soft material. Sound reflects really well of hard materials. It's the same as, and probably for most of you, it's something you've heard in a movie. I haven't actually experienced this personally. One day I hope to. You go to a large, deep mountains range and you've got a big valley in front of you and you shout at the top of your lungs and you hear your words come back to you. You hear an echo. That echo is the reflection of your sound off the mountain, off the walls, off the rocks, because they are hard substances, okay? To hear a nice echo, to hear an echo that's sharp and crisp, and actually you can distinguish what the sound is, you need to be at least 30 meters from the surface that's reflecting it back. Otherwise, you just hear a form of what we call resonance, and it sort of makes it all fuzzy. So you know it's there, but you can't really make out what it is, okay? But why is this important? It has an important application for humans and for animals. But first we're going to look at humans. The first application is in sonar. You watch a movie, you watch submarines, okay, and there's someone who's got his earphones on and he's watching a little screen and you see a little light go around and then you hear this blip and it's beeping all the time, okay? It's a form of radar, but it actually is sonar. Sonar is what is known, and this is what it stands for, is sound, navigation, and ranging. It is using sound to determine distances. What happens with sonar is, with a submarine, for example, they have a device attached to the submarine that lets out a very high frequency sound that we can't hear, which is good. It does not harm the animals in the sea, so it's not dangerous to the fish life. That sound then goes out and then hits a barrier, the bottom of the sea, another ship, another submarine, whatever the case may be, it hits a barrier. By hitting that barrier, it's then reflected off the barrier and returns to the submarine that sent it out. That returning signal goes through a special machine, which then translates the time it took for that sound to go out and come back, knowing how fast sound travels in water, and tells the man who's working the sonar that there's something so many meters, so many kilometers away from them. That's nice and easy. That makes it fun for them, okay? It's a good way to track things. But what else we use it for? Well, it's also used for mapping the ocean floor. Some parts of our oceans are so deep, we cannot physically as humans get there. It's just too deep, and the water pressure would be too much. So they use big ships, big important navigation ships that have lots of very specialized equipment. They do the same thing, where they send out a sonar, send out a special frequency wave, sound wave, which goes down, hits the bottom of the ocean, and then comes back up. And they can calculate the distance from the bottom of their ship to the ocean floor. And as the ship moves along, they start to build up a picture of whether the ocean floor gets lower, whether it comes up, whether there's a mountain range. So they're able to map what the ocean floor looks like, particularly in the places where we can't reach because it's just too deep. And that's great for us. We like that. I mean, we have this ability to really see through the use of sound. But what about animals? Animals use this as well. And in fact, a very special animal known as a bat uses this. Now, I'm not a big fan of bats. They scare me a little, I have to be honest. But they use a system called echolocation. And what I'm going to do, I'm going to show you a quick animation to show you what happens, okay? So what we have here is we have the bat. It's trying to find a moth, and we're going to show the waves as sound waves as circles. The sound waves come out. The bat leads off this really, really high-pitched sound. That sound then travels back to the bat's really super fine hearing, and the bat instinctively then knows where that moth is and how far away it is. It's how they can see. Okay, bats are pretty much blind, but they see through their sound. And in fact, and this I find quite incredible, I'm hoping you've seen this, this has become a new technique that humans are trying for blind people, where they use a form of echolocation. Because remember, when you lose one of your senses, often another sense will become even super sensed in a way, and their hearing is really, really good. So they use a form of echolocation. And either they use an instrument which forms the sound, or they do it themselves. And it's actually quite incredible to watch, because then they don't need to use a cane. So we're using a little bit of what bats do, which is what they were created to do, and we're translating it into a human form, which is also very exciting, okay? Bats aren't the only animals that use echolocation. Dolphins use echolocation, okay? A lot of mammals do, because it's a good way of seeing something that no one else is going to see, or to be aware of what's around them the whole time, okay? As a teacher, I would love echolocation, because then I'd know exactly where all my students are all the time, even when they're trying to hide. But this is great. So we know that sound is a transverse wave, a longitudinal wave. What am I saying? Sound is a longitudinal wave. Sound has to be produced through the vibration of something, okay? Which means sound has amplitude, it has wavelength, it has frequency, and it has period. But what does that mean for us in terms of what we experience as sound? This is actually quite important for us, because when I was playing with my toys, I can do, for example, if we look at my claves again, I can make a soft sound, or I can make a loud sound. Now, it's a little hard to hear the pitch, but they were actually the same pitch. What does that mean? One was soft, one was loud. That's true, that's easy, but the pitch is the frequency. So a high frequency, my triangles make a very high frequency sound. Got that high pitch. These make a much lower frequency sound. The harder I hit them, the greater the amplitude. Remember, the sound is formed when we have a vibration movement. Okay, that's where the sound is formed. So if I hit them really hard, they're going to vibrate more. So it gets louder. How do I show you this? Well, what I have here is a little instrument. It's an electronic tuner, which I've brought in simply because it's important for us to be able to hear the difference between pitch and sound, okay? Now, what I'm going to do is I'm going to switch it on. At first is a little annoying to start off with, so we're going to switch it on because I need to change, and we're going to turn the sound off, okay? Now, this is going to produce, and at the moment it's producing a C note, which is a frequency of 441 hertz, okay? The sound's off. You can't hear it. Certain frequency sound. As I make it louder, you can hear it very softly, and we make it louder and louder. It's the same pitch. It's very annoying. Okay? It's as loud as it's going to go. I changed the amplitude of the wave. Same pitch, same frequency. Very annoying one, actually. Same frequency, different amplitude. If we now make it, what we're going to do now, I need you to listen carefully. I'm going to change the pitch. So I'm going to change the frequency. So we've got the sound, keeping the volume the same. It's a little higher. It's a little higher. Even higher now. And this is just going through the scale. And it gets higher. And it's going to come to an end soon, I promise. Now it goes back to the beginning. Okay? So if we look at that, I'm hoping you'll hear it. We're going to do this. We're going to go back to that high one. Very high, quite low. Different pitch. Same volume. I haven't changed the volume. It's a different pitch. Okay. So what I want you to see there is that your amplitude, maximum displacement, loudness. Okay? And you all know that. Some of your friends have very soft voices. And some of them are very loud. Okay? Same with your teachers. Teachers tend to be on the loud side. The pitch is the frequency. Okay? How high it sounds. When you think of a vocalist, a singer, someone like Mariah Carey has a very high-pitched voice. Okay? Someone like Barry White has a very low-pitched voice. He's a baritone. Okay? Those are important things for us to know. But what can we hear? Because everything I've just shown you, that's within our range of sound. Sound can range from being 10 hertz to being 1,000,000 hertz if we wanted. We can't hear all of that. Animals can't hear all of that. But if we look, and I've got a table here for you, humans can hear as low as 20 hertz, but we can only hear as much as 20,000 hertz. It's quite a small range. Dogs only start hearing from 50 hertz. That's quite high, actually, compared to what we can hear. But they can hear up to 45,000 hertz. You've all seen those dog whistles where you blow, we can't hear it, but the dogs go mad because they can hear it. Cats, from about 45 hertz to 85,000 hertz. That makes them very good hunters, by the way, because they can hear very soft sounds. Bats, 20 hertz to 120,000 hertz, which makes sense because of their echolocation. Dolphins can hear as little, as small as 0.25 hertz. That's incredible. They have an incredible range. Goes up to 200,000 hertz. Look at elephants, though. Elephants start at 5 and end at 10,000 hertz. So they don't hear high-frequency sounds very well. The bigness of their ears doesn't determine what frequencies they can hear. Okay? Just means they can capture a lot of sound, but they can still only hear certain frequencies. So, what we're going to do now is we're going to look at a couple of questions, and then we'll take a short break before we do calculations. Here we have a diagram. It says, study the following diagram represents a musical note. Redraw the diagram for a note with a higher pitch, that is louder, that is softer. Now what I'm going to do is I'm going to actually draw it on my diagram, because then it's going to make it a bit easier. Higher pitch means higher frequency. Frequency means that here I've got two waves in this time frame. I need to make sure that now there's more waves in that time frame, but the amplitude must stay the same. So when I draw this in, let's do this one in green. The amplitude of the wave is going to be the same as the one I've got now. Can't change. It's also why I'm using this, so you can see exactly what I'm doing. It goes up and down, much higher frequency. Ooh, and I'm going to, let's make sure it goes all the way to the top. Okay? More, and it's not the most regular wave in the world, but it'll do. Higher pitch, so which means higher frequency. High pitch sounds generally are quite annoying though, let's be honest. What about louder sound? Louder means bigger amplitude, bigger displacement from rest. So if we do a louder sound, let's do this. Now watch what I have to make sure happens. It goes through the rest position at the same time. So the frequency, let's just quickly do that, is going to be different. Is going to be the same, sorry. Okay. Higher amplitude, but gets to the rest position at the same time. We're not changing the speed. We're not changing any of those things. If now we have a softer sound, it's a smaller wave that needs to follow the same pattern. Softer sound. Okay, same number of waves, same frequency, smaller amplitude. Higher pitch, higher amplitude, louder sound, higher pitch, sorry, greater frequency, louder sound, higher amplitude, softer sound, softer amplitude. Okay? We are going to take a short break there, because what we're going to do after we come back, because lots of information overload, is we're going to look at some calculations, and we're going to look at a couple more applications of sound, which is very exciting. So we'll see you in a couple of minutes. Welcome back. When you went away, we just looked at pitch and amplitude and all those sort of wonderful things. Now we need to do some calculations with sound. Sound's a wave, just like the longitudinal waves we've been dealing with, just like a transverse wave, which means the wave equation still applies. So let's look at an example. And actually, this is a nice example because we've had a lot of thunderstorms lately, okay? And sometimes you want to know, is it getting closer? Is it going far away? And it's something very unique to us. Now, a lightning storm creates both lightning and thunder. You see the lightning almost immediately because light travels at 3 times, let's not write over it, shall we? 3 times 10 to the 8 meters per second. After seeing the lightning, you count 5 seconds. And then you hear the thunder. Calculate the distance to the location of the storm. Now, is the fact that they gave you the speed of light important? Not at all. Because it's not the speed of light that's important, because the light's going to get you really quickly. It's what they told you about what you hear. Now, what we're going to do is we're going to make an assumption about the speed of sound, and we're going to say, assume that the speed of sound is 340 meters per second. Okay? Can't be 343 because it's not at 20 degrees, it's a thunderstorm. It's definitely not 331, so I'm telling you, let's make it 340. But they tell you it takes 5 seconds before you hear it. Can we use the wave equation? I'm hoping you're screaming and going, no, not really, because that's not period. They're not saying to you that it takes 5 seconds for one sound wave to reach you. It takes 5 seconds for the sound to reach you, it is already traveling at 340 meters per second, which means we're going to have to use the equation we used for transverse waves and transverse pulses in the last lesson, which said to us that speed is distance divided by time. So our speed is 340. My distance is what we're looking for. And my time is 5 seconds. So we go, well, actually, we can do that. That's nice because the 5 seconds is at the bottom. So remember, you don't have to show me the step. I just want you to all see what we're doing. So distance equals 340 times 5. And we're going to quickly calculate it. 340 times 5. We get 1,700. Ooh, pen. That means it's 1,700 meters away from you. Okay? How many kilometers in that? Just as a little extra. Remember, 1,000 meters in a kilometer, which means it's 1.7 kilometers away. That's still quite close, just so you know. It sounds far, but for a storm, that actually is quite close. So if you are seeing thunder and hearing lightning that close together, you really need to make a plan to get indoors, and you shouldn't be playing on fields and playing in the rain because lightning can be very, very dangerous. And remember, lightning can kill you. So we want to avoid lightning if we can. Okay, so another question. Sound cannot travel in space. We know this. Discuss what other modes of communication astronauts can use when they are outside the space shuttle. So now we go, darn, we can't use sound. That means we can't look at each other. Even if we're right next to each other, we can't have a conversation. Plus, of course, astronauts are in suits and things because if they don't have their suits, they can't breathe, and it's really cold in space. So they'll freeze to death, and they'll suffocate. So that's bad. So what astronauts actually do is they use radio waves. Radio waves is not a sound wave. It's an electromagnetic wave, and it's a very special type of wave. And we're actually going to look at it in the next session, in that radio waves fall into the same category of waves as light does, and they can travel through space. So they use radio waves. They talk into a microphone inside their helmets, okay? Though that microphone is connected to an electrical circuit with a battery, which then converts it into a radio wave, and that radio wave can travel through space to their friend. Their friend then has a receiver, picks up that radio wave, converts it back into an electric signal, which then they can hear. So that just makes so much sense because they have to make some plan, okay? They cannot just talk to each other. All right, now, we've looked at a short calculation, but before we do some more calculations, let's just quickly talk about some applications of the use of sound, specifically the use of ultrasound. Now, ultrasound is sound where the frequency is greater than 20,000 hertz. We can't hear it, but I'm hoping ultrasound is something it's a term that you've heard, that you've sort of heard somewhere along the line, because often what an ultrasound refers to is what a lot of mothers will refer to is when they go for an ultrasound when they're pregnant. What an ultrasound does, and it's very exciting, and I have a lot of friends who have been pregnant recently, so I'm seeing lots of these little pictures at the moment, is the doctor has a special machine that works almost like a sonar does with a ship. That machine has a source of ultrasound that produces the sound wave that they then put on the mommy's tummy. As they move the machine along, that ultrasound goes through the mommy's tummy and her skin and all the fluids in there, and it reaches the baby. Then when it reaches the baby, it reflects back off. The machine receives that sound, calculates how long it took for the sound to come back, and then translates that into an electronic signal, which then becomes a picture. And we get a clear picture of what a baby looks like inside the womb, okay? And I'm sure you've, at some stage, I hope, you've either had a parent or a sister or a friend who's been pregnant and they've come to you and they've shown you their first ultrasound, and there's this tiny little speck. And you go, that's gorgeous, even though it's a little speck and looks like a peanut. Okay, but that's what it is. There's your baby. As the baby grows inside the mommy's tummy, those scans get more and more detailed because there's more detail that's been formed with the little body inside it. Why do we use ultrasound, though? Because surely we can get a much better picture with X-rays. Because ultrasound doesn't harm the baby and doesn't harm the mother. X-rays are extremely dangerous for a mom and very dangerous for babies, which is why if you ever need to go to a hospital and get X-rays, and for the girls, they'll ask you this, is there any chance that you are pregnant? Because if you are, you can't have an X-ray. They have to find another way they'll do a CAT scan, okay? Because X-rays are extremely bad for fetuses inside the womb. So we use ultrasound then to create images of babies. But we can also use ultrasound in industry. When engineers are looking at metal for construction, they have, especially if it's a very big building and they need lots of metal pipes and strappings and all sorts of things, you want to make sure that your building's not just going to collapse on you because you didn't see a crack somewhere in the metal, which can be very hard to see with the naked eye. And engineers have a machine that does almost the same thing as an ultrasound machine does with humans, in that they can put it on this piece of metal and it's able to pick up the cracks as it goes through. So it can pick up if there's a crack in the metal that might cause damage or eventually might expand because of the natural expansion and contraction of the metal in an everyday because of heat and cold and all the rest of it, that they know they can't use that piece of metal or they have to replace it. But it uses ultrasound, which is also quite exciting for us because then we know we have this ultrasound that shows cracks in metals, which we could never pick up with a microscope. Plus, the practicality of trying to take every piece of metal from a really big building under a microscope, it's never going to happen. Ultrasound machine does that. Another use is for cleaners. When you have ultrasound cleaners, they're sometimes called supersonic cleaners, they use sound between 20 and 40 kilohertz, 20 to 40,000 hertz. Now, what they're used for is for cleaning jewelry. You don't want your expensive jewelry to be put into a base or an acid or something that can corrode it, okay? It's used for cleaning lenses on a very expensive surgical equipment, on telescopes, that sort of thing, okay? Watches, dental instruments, sound, ultrasound, supersonic cleaning is used for sterilization. So it's actually quite exciting to know that we have this sound, we have this ultrasound, but besides being able to make pictures of babies, we can clean things. We can do a whole bunch of stuff with it. And it's not just, and it's better for the environment. Let's just be honest. If we can use a supersonic cleaner rather than a corrosive element or a corrosive cleaner like sodium hydroxide or Jick or bleach or anything like that, how much better for our environment, which we know is an important thing that we need to be looking at all the time. So, a little bit of extra for you. What we're going to do now, in the last few minutes that we have, is we're going to do some calculations because we've done a lot of theory, we have done some calculations, now we're going to spend a little time doing some more calculations together, okay? So I'm hoping you got your thinking caps on, you got your calculators and your pens, and you're ready. So, let's look at question 8. It says to you, an automatic focus camera, which is your normal everyday camera, uses an ultrasonic sound wave to focus on objects. Another use. The camera sends out sound waves which are reflected off distant objects and returns to the camera. You can't hear this, it's ultrasonic, okay? A sensor detects the time it takes for the wave to return and then determines the distance an object is from the camera. These first 3 or 4 sentences, grade 10s, this is to put your science in context. I could have just started this question by saying a sound wave returns to a camera or returns to a source 1,015 seconds after leaving the camera. How far away is it? That's boring. Let's put it in context. That's why you have these. But it does mean that this first little bit of information really isn't that important to the calculation. But we've got to find that information. So now, the sound wave, which has a speed of 344, so let's write that down. Returns to the camera in 0.15 seconds after leaving the camera. How far away is it? So distance. Okay, now, very important. I'm going to draw a little diagram because what they're saying to you, there's my object, camera's over here. The sound wave goes out and comes back in 0.15 seconds. All I want to know is what is this distance. So, we need to make a decision here. Let's use the information as it is and decide what it means for us. Velocity, speed, is distance divided by time. So we're going to have 344 distance, 0.15 seconds. Okay, 0.1. Okay, that means distance times both sides by 0.15. And we get, we're just going to do this in a second, 51.6 meters. Okay? But now, what has actually happened is the wave has traveled there and it's traveled back 51 meters. That means I've calculated double the distance because the time taken was there and back, and I just want to know what there is. So, the actual distance, I can actually spell, let's spell it right, shall I? Distance is equal to 51.6 divided by 2. It's 25.8 meters. The other way around you could have done this question, grade 10s, is you could have taken the time and divided by 2 straight away. And gone, well, it's gone there and back, so if I only want there, then it's going to be half the time. You always make the assumption that the time to get to the distance is equal to the time to get back. If that isn't the case, then we need to give you more information, and then the maths gets all hairy and horrible, and we're not going to do that. Never happens at school level. Okay? You ready for another one? Let's go to next question 9. Question 9 says to us, calculate the frequency in hertz, that's nice, and wavelength. They're asking you to calculate 2 things. Let's just quickly note that. Frequency, so that's the first part of my question, and wavelength. That's the second part. Of the annoying sound made by a mosquito when it beats its wings at an average time of 600 beats per second. Assume the speed of the sound wave is 344. Well, I'm going to need to know frequency before I can calculate wavelength. They've actually given me frequency in the question because they said to me that the mosquito beats its wings 600 times per second. The frequency is 600. Hertz means per second. So when we look at the wavelength, the frequency, sorry, it's the time it takes for it to do one, how many beats, how many flaps up and down. That's 600. So first part of the question sorted. 600 hertz. You don't have to do anything else. Velocity, speed, 344 meters per second. Brilliant. What are they asking you for? Wavelength. So, speed is wavelength times frequency. You're welcome to manipulate the question first, but I don't suggest it. So this is 344 We want the wavelength. Frequency is 600. We divide both sides by 600. And that means we're going to have 344 divided by 600, and we get 0.57 meters. Okay? It's quite a small wavelength still. It's half a meter. It's about this big. A little bit bigger. Okay. Well, actually, that's quite a big wave still. But it's a very high frequency. 600 hertz is a very high frequency. That's why it's so annoying. Okay, we don't like high frequency sounds. They're not fun for us. Ready for another one? Oh, good. So, a person shouts at a cliff, because we can, and I promise you one day if I ever get to somewhere where I can do this, I will. Here's an echo from the cliff 1 second later. Speed is 344 meters per second. How far away is the cliff? Once again, let's quickly draw a little diagram of what they're saying. Here's my person. Here's my cliff. Person shouts, their sound goes to the cliff, comes back from the cliff in 1 second. So let's do this one a little differently to the one we did last time, because last time we looked at distance and all sorts of things, and then we changed it around later. We're now going to divide time in half to start off with. Okay, so that's what we're going to do. So what we're going to do is this time, instead of calculating the total distance and then remembering to divide it in half like we did last time, what we're going to do is we're going to take the time and we're going to recognize, okay, it takes 1 second to get there and back. So if the total time is 1 second, the time to the cliff is half that. Okay. And 1 divided by 2 is a half. So we have half a second. We have our time. Brilliant. Velocity, speed, is 344 meters per second. What are we looking for? Distance. Well, we have all the information we need. Time, speed, want distance. Equation, speed equals distance over time. Which means, and no, I'm not going to write it like that. That's a bad way to write an equation. Please don't ever do that. Okay. My speed is 344. Distance is what I'm looking for. Time is half a second. Okay. How do we get distance on its own? We're going to times both sides by a half. So it's 344 times 0.5, and on your calculators it's the same as dividing by 2. Okay, so hopefully all your calculators out and you're doing it, and you're going 344 times 0.5, and we get 172 meters. Done. In total, because the sound traveled for only 1 second, it's going to have traveled 344 meters. But we weren't interested in that. We were interested in what is the distance from the person to the cliff. Okay? You ready for one more? I hope so. Okay, so we're on to our last question, and it's actually a really nice question. It's not one that you see very often anymore in your classes, but it's a nice way to make sure that you sort of got all the theory together. So what we have here is we need to select a word from column B that best describes the description in column A. So I think we've got all the, okay, we've got music and sound and waves. We'll do those in a second. So let's ignore column B before we start this. It says to us, the first thing is waves in the air caused by vibrations. This is the same, and it's actually a nice exercise for you, because in your tests and exams, you also get asked one-word answers. This is where we test all your theory. It's another way for me to do it. So they're asking me, what is the term I would use to describe a wave caused in air by vibrations? Ooh, hang on. We've just done it. Sound waves. So that one's E. Sound waves. That was easy. Don't even have to think about it. Number 2, Waves that move in one direction, but the medium moves in another. It's not the greatest description, but what they're saying to you, for example, is the wave's moving this way, but the medium's doing this. They're not moving together, okay? And if you look at this, you go, hang on, wait, perpendicular, that's a transverse wave. So that means we go and we find transverse wave. I'm going to cross this one out because it's not an option anymore. That's G. Transverse wave. Don't need that one anymore. Brilliant. Number 3. Waves in medium that move in the same direction. In other words, medium goes this way and the wave goes that way. We've just done this. What we've been doing for the last hour or so. That's our longitudinal waves. So we look and we go, there it is. It's A. So number 3 is A, and we can get rid of that. Number 4. The distance between consecutive points of a wave which are in phase. In phase, distance between them. And consecutive. This is another definition. Hopefully you're screaming at the TV right now going, I know what that is. That is wavelength. So we look on our column B and we go, where's wavelength? It is H. So that is H. Brilliant. Question 5. How often a single wavelength goes by? So what we're looking at here is we're looking and we say, okay, well, if I'm looking at time and the waves can pass me and I'm looking at how often, we're looking at the frequency. How often? Okay, so now we look at our options and frequency is right here. It's number B, so we can do frequency. There we go. Then, half the difference between the high points and the low points of the waves. This we really need to draw a diagram for because this can be a little difficult to actually just visualize if you don't. So let's draw a diagram. And here we have our wave. Okay, we have more than one, but that's fine. And they're saying to us, if I look at the distance from the top of this point to the bottom over here of my wave, and I say, okay, that's half the that's the difference in distance. But now I say if I take half of it, this point, what is that? And I'm hoping you'll go, oh, but that's easy. Drawn like that, it's easy for me to see because it's the distance from the rest position to the trough, or the distance from the rest position to the amplitude, to the crest, which means it is the amplitude. Okay, that means we've used D, and we can put that there. Number 7. The distance a wave covers per time interval. What they're saying to you is, if I had said to you, what is it when I describe it as being that the wave covers 10 meters in 1 second, 10 meters per second, or it covers 100 meters in 3 seconds, I'm asking you about its speed. So that's K, wave speed. So we're actually almost done. We used wavelength a little bit earlier, and we didn't. So let's just make sure it's there. Number 8, the time taken for one wavelength to pass a point. In other words, we're looking at a point, we have a stopwatch, and the top of the crest comes past, we press start on the stopwatch, and we watch, and we watch, and we watch, till the start of the next crest comes past, and we stop the stopwatch. What have we done? We've measured the period of the wave, C. Okay, so we've measured the period of the wave. This was a great question because this question really brought together all the important terminology that you've learned over the last 2 lessons, which is so, so important. Okay? We have finished sound and longitudinal waves. Remember, a longitudinal wave is characterized by the fact that the particles move backwards and forwards and parallel to the direction of motion. Okay? When the particles are close together, we have a compression. When they're far apart, we have a rarefaction. The amplitude is described as the maximum displacement from the rest position. So when a particle either goes one way or the other side, it's still maximum displacement. Wavelength is still the distance between 2 consecutive points in phase. So the beginning of a rarefaction to the beginning of the next rarefaction, or the beginning of a compression to the beginning of the next compression, as long as they're in phase. The wave equation still holds. Speed equals frequency times wavelength. Frequency is related to period, where frequency is equal to 1 divided by period, and period is equal to 1 divided by frequency. And of course, sound has lots of applications: sonar, ultrasound, echolocation with bats. And then we also looked at the difference between pitch and loudness, where pitch has to do with the frequency of the sound and loudness has to do with the amplitude of the sound. Okay? And that's where we're actually going to end today's session. Next time we're actually going to look at electromagnetic radiation, and we're very excited. So we're going to say goodbye for now, and we'll see you next time.